Today's speaker is Jonathan Makela. He is a good friend and co-instructor of mine. Jonathan explores the atmosphere at the very edges of what could be called atmosphere. And that work, looking at what happens on the very edge of space, has surprising implications for what happens right here down on the ground.
Is that me?
I'm walking over here. Just not that much, that's right. Jonathan is a 2003 graduate of Cornell University with a PhD and immediately joined the faculty here, is that correct? Oh, that's right. That's Naval Research Laboratory, for those of you who don't know. And he has been here ever since. He was recently promoted to full professor, has a collection of honors and distinctions too long to list, but included among them are many, many teaching awards, and so our expectations are high. Jonathan today will talk to us about earthquakes, tsunamis, and space. Thank you. Jonathan Makela.
All right, thank you, Scott. Can we turn it down a little bit, Wally? So, as Scott said, I've been here for about the past 10 years, and a lot of the work I do is based on sensing the near space environment and trying to understand how looking up can tell us important things about things going on Earth and how the near space environment affects technologies such as communication satellites, GPS, and the like. What I'm going to talk about today, though, it seems a little bit separated from that. I'm going to talk about earthquakes and tsunamis, but importantly, about 4 years ago, 4 years almost to the day, it was March 11th, 2011, we had the Great Tohoku earthquake. And this was really, in my career thus far, a very serendipitous event for the fact that we were able to see in some of our instruments a signature of something we were not expecting at all. And this has really led to a new chapter in my career, studying a different type of physics with the same sort of sensors that I was using for studying the effects on GPS and satellite communications and the like. So for me, from a personal standpoint, this is a story of discovery and how we really want to be looking outward because we never know what we're going to see. We never know what we're going to learn. And so we should always have our eyes and our minds open so that we can always be learning. So what I'll do today is essentially, and the first point I don't think I need to do too much of, but essentially motivating why it's important to study tsunamis. Clearly it can have a lot of effects on humans and the environment, but we'll talk about that in a little more detail. But then I'm going to step back a little bit and talk about what a tsunami is. I think there's a lot of misperceptions about what a tsunami is and what it isn't. So I want to make sure we're all on the same page in terms of what we're talking about. And then I'll move into how we currently monitor for tsunamis, how we detect and predict whether or not an earthquake is going to cause a tsunami and whether that tsunami is going to be a hazard or not. And then the second half of my talk is going to be the meat of, well, how can we use measurements in the atmosphere or of the atmosphere to monitor and perhaps predict tsunamis and whether or not they will be hazardous to human population. So in terms of motivating, this is a list I just grabbed off of Wikipedia because that's an easy thing to do, although I tell my students not to do that. Of about the 10 most destructive tsunamis in history. And you can see that they cover quite a few centuries. We go all the way back to some early observations in 365. So we can determine these through written records and through the geological history. But an important thing is the death toll can be tremendous, which of course is one of the reasons why we're concerned with monitoring and studying tsunamis. But the other thing to note is that other than the Indian Ocean, the Sumatra tsunami in 2004, most of these are way back in history. And there's actually a large gap between maybe the 11th or the 12th with maybe 10,000 deaths and all these for about 50 years or so. And that was right when we started to monitor for tsunamis using ocean buoys, and we'll talk about that in a little bit. So really monitoring and being able to give a clear warning to people that they should go to high land or take some other precaution has really helped lower the death toll of most of the tsunamis that occur this days and age. However, as we saw with Sumatra and as we saw with the Tohoku earthquake and resulting tsunami, that may not, the warning systems, the monitoring systems aren't perfect yet. And so what we'll be talking about is a new way where we may be able to hopefully improve those sorts of monitors for future tsunami events. So the Tohoku earthquake in 2011, 4 years ago, generated a devastating tsunami. It reached the coast 6 minutes after the earthquake. So that's about the time that it took for the earthquake to generate the tsunami to reach the coast. 38.9 meters was the highest record of the ocean wave as it came inland. And we'll talk a little bit about the physics behind generating waves of that magnitude. But that's 120 feet. So just imagine a wall of water coming towards you that's 120 feet tall, and you can imagine the devastation that these things can cause. They can lift boats, and this boat probably wasn't supposed to be on top of that building. That building is 2 stories tall, so you can really get a sense of the energy, of the power of these waves. Clearly, there are quite a few death tolls, but I think the reason why we're familiar with the Tohoku tsunami so much is the devastation it caused due to the Fukushima nuclear power plant disaster. So it wasn't the earthquake that caused the disaster there, it was the tsunami that overwhelmed that power plant. And quite a bit of financial toll, okay? And of course, it's not just the near field that is affected by these tsunamis. You know, an earthquake is going to affect the region that's very close to the earthquake. The tsunami propagates all the way across the ocean. Within 24 hours, there were 2.5 meter waves observed in Russia, Hawaii, California. There was a harbor in Southern California that these waves caused a lot of damage for the boats that were moored in that harbor, $50 million worth of damage in the harbors in California. So these sorts of events are not localized. They're global almost in nature, which again motivates to why we need to study them. And it's not just a problem for the people that live near where the earthquake occurs. It's a problem for anyone that lives near the ocean. Okay, so tsunamis cause massive amounts of destruction. I think that's clear. Here's another movie. This is again of the tsunami and the result of the Tohoku. You can see all this water. It's washing over fields. Here we have an irrigation ditch. So these waves, as they come in, the amount of energy starts to destroy buildings. You get all this wastewater. If it goes over a sewage plant, this salt water is inundating over farmlands, and we know that's probably not good for the farmlands. So it's not just the immediate destruction. There's actually a lot of devastation in the aftermath as you have dysentery problems, water sanitation problems, infectious diseases. In fact, with the 2004 tsunami, many of those deaths were in the aftermath, days and days after, as the health of the regions that were affected deteriorated over time. Here you got a nice boat that's going. Again, it's being moved inland. And so you can just see it's perpetual. It's not a quick wave. It's just an inundation of water as you go. You have people driving their cars. They probably shouldn't be doing that. And so the devastation isn't just instantaneous. It's a long-term devastation that can occur. So as I said, we can contaminate the drinking water. That can lead to spreading of diseases. It has environmental impacts. Just think about the land animals that are that are living away from the ocean. They're now inundated with water. So there have been reports of mass deaths of drowned animals that can't swim, and then of course the huge financial loss that's associated with the tsunamis. So I think it's clear that we really want to be able to understand the tsunamis. We do understand tsunamis. We know the physics behind them. And so monitoring and predicting the events is really what's going to be important as we move forward here so that we can mitigate these impacts. Okay, so what is a tsunami? So a tsunami is not a tidal wave. This is one of the misperceptions, and when I started learning about these, I think in my mind I thought tsunamis and tidal waves were sort of the same thing. Tidal waves are caused by the gravitational pull of the moon, the sun, and other planets. All right? And they have, we'll talk about the properties of various waves, but they have different periods, different wavelengths, different amplitudes than tsunamis do. Tsunamis are not the same as ocean waves, right? You go stand on the shore and you see these waves 6 feet tall, they come crashing and yeah, they knock you down. Okay, there's energy in them. But they don't go inland and inland and inland and inland. Okay? Ocean waves are caused by the movement of wind over the sea surface. And again, they have different properties than tsunamis do. Okay, so just a primer on waves for those of the younger members of our audience. So there are lots of different waves, but they all can basically be characterized by the wavelength, which would be the distance between successive peaks in the wave. They can be characterized by the amplitude, which would be the height of the wave, so how large that oscillation is. And then they can also be characterized by their period, which would be if we watch this wave travel, there's one period, there's another period, there's another period. So there are other ways to characterize them, but they can all sort of be tied into these 3 different parameters here. And so if we understand or measure the wavelength, amplitude, and period, we can calculate things like energy and power. We can talk about velocities, frequencies, and the like. But they all tie into those parameters there. And each of the different types of waves in the ocean have different ranges for these 3 parameters. All right, so tidal waves. This is a nice little plot to help us. So along this axis are the wave heights in centimeters, and this is a log scale, so every tick mark here is an order of magnitude or a factor of 10 larger. And then we have the wave period here in terms of seconds and minutes and hours. So tidal waves, there are these waves here, so they have periods that are quite large, right? They're caused by the gravitational pull of the moon and the sun. The Earth rotates every 24 hours, but there's actually a harmonic at 12 hours and 24 hours. So those are your tidal waves. They're quite long periods, and their amplitudes are on the order of several feet or so. I'm mixing MKS and imperial units here, I'm sorry. There are some notable exceptions of that wave height. There are much larger tidal effects, like in the Bay of Fundy up in Canada and the like. But in general, they're sort of on the order of 3 feet or so. Ocean waves are sort of in this box right here. They're caused by wind blowing across the ocean. You can see the periods here are quite short, tens of seconds, maybe up to a minute or so. And they can have amplitudes of several feet, as I said. You can stand at the ocean and you can have waves that wash over you that are much taller than you. Tsunamis, however, fit in this nice little window in between tidal waves and ocean wind waves. You have periods on the order of tens of minutes, maybe up to an hour or so. But really, I think 10 to 30 minutes is where I would put it. And on the open ocean, and that's an important caveat there, the amplitude is very, very small, tens of centimeters. Okay? The ocean amplitude is not that large, not at all. But the period and the wavelengths are what are going to be very important here. So what is a tsunami? Derives from the Japanese word for a harbor wave, tsunami. And this comes from the fact that in centuries old, they would stand and they'd see this wall of water fill up their harbor, and then 30, 40 minutes or so go away. They're generated by the rapid movement of huge, huge volumes of water. Typically, we think of them as being caused by earthquakes, but they can also be caused by a sudden landslide on the ocean's shore, which would displace a lot of water. Volcanic eruptions, same thing, especially if that volcano is suboceanic. And even a meteorite impact. If you have a large meteor come and hit in the Gulf of Mexico, that would launch a tsunami across the Gulf, Florida, Louisiana, Mexico. This produces a small amplitude wave, importantly having very long wavelengths. So again, the wavelength being the distance between successive peaks. Again, think about the ocean waves. Those are very short wavelengths, maybe feet or so. The wavelength of a tsunami is hundreds of miles. And that's the important part. Even though the amplitude is very, very, very small, they contain a lot of energy, a lot of water, because that wavelength is so incredibly long. So even though they have small amplitudes, they're devastating because the wavelength carries a tremendous amount of energy, and it's affecting the entire water column all the way down to the surface of the ocean underwater. And so you think about the deep part of the ocean, which can be a mile to 3 miles deep. You're moving all of that water in the tsunami as it moves across the ocean. So a tremendous amount of energy. The other important part is the rate of energy loss within a wave is very, very small for these long wavelength waves. So whereas a short wavelength is going to deposit its energy and won't affect very large regions, these waves that have very long waves, they're going to carry their energy all the way across the ocean surface. The wavelength of the tsunami is longer than the ocean is deep, right? Hundreds of miles versus a couple miles deep. So this means that a tsunami wave is what we would call a shallow ocean wave, shallow water wave. And its speed is proportional to the depth of the ocean. You work through the math, they move fast, 900 kilometers per hour. That's faster than a jet airplane. So they're moving with tremendous speed. So all these things coupled together are just going to say there's a lot of energy here. And that a tsunami can travel all the way across the entire ocean within a day. And so it's affecting the entire ocean basin, not just the region where it was generated. The other important part is that, again, remember the speed is a function of the ocean depth. So as that wave starts to get towards land, the ocean depth decreases and the velocity of the wave is going to slow down. But you still have this long wavelength wave behind it. So you have a fast wave starting to approach the start of that wave, and it's going to start bunching up on itself. And so as the tsunami reaches land, it starts to slow down. The wavelength starts to get much smaller, right? So here's the ocean depth out in the open ocean. If we had something that was 190 miles wavelength, traveling as fast as a jet engine, as it gets towards the shore, it slows down, and the wavelength gets very, very small. Well, 5 miles is still quite big, right? But compared to 190 miles, it's quite small. And so as this compression is occurring, the energy in the wave is still there, and it has to go somewhere. And so what it will do is the amplitude of the wave is going to increase. So we have these tens of centimeter waves on the open ocean. They start to become very, very, very large, up to those 40 meters or so that we saw in the Tohoku event. And so that's how you translate this very, very small ocean wave into these devastating waves that we see when they reach land. And then remember, we still have quite a long wavelength, so anything that is below 30 meters elevation within 5 miles of the shore is going to see this wave as it comes in. If you were here before we started the lecture, you saw this one movie of a harbor, of a channel of water, and the water just keeps on coming, and you start to see boats and cars and vans and houses being moved by this. And again, that's due to these the increase in the height here and the long wavelength. So that benign tens of centimeter wave becomes something that can be devastating, carrying a tremendous amount of energy as it moves inland. Okay, so that's the basics of a tsunami. So how do we go about monitoring tsunamis these days? Early detection is key, right? You want to be able to provide people with warning so that they can take the proper caution and precautions that they need to. Fortunately, most of the tsunamis that are developed are caused by events generated in the solid earth, earthquakes, volcanoes, and the like. And there are large networks of seismographs around the world that can detect the waves associated with those earthquake or those seismic events very rapidly. And these days, within a minute or two of when an earthquake happens, the USGS, United States Geological Survey, and the related associations around the world can pinpoint to within a few kilometers where that earthquake occurred, what its amplitude is, what its frequency is. So they are very good at pinpointing the location very quickly. And if the location where they pinpoint the seismic event is under the ocean, there's a potential for a tsunami to occur. However, until you actually make a measurement, you can't tell for sure whether a tsunami is going to result or not. Okay? We're not at that stage where we can just look at that initial observation and say, definitely there's going to be tsunami with these characteristics. we have to make some sort of a measurement of the ocean surface displacement to be able to determine whether a tsunami has been launched. And that can take time. We monitor them using a network of buoys. So these are open ocean buoys that can measure the rise and fall of the ocean over time. And if you have an earthquake and it does generate a tsunami, once that tsunami moves past one of these buoys, you'll make that measurement that will tell you whether or not a tsunami occurred or not. Okay, so this is the measurements from a few days ago from the ocean buoy located off the west coast of Hawaii here. And we can see here over the course of a few days, these are in meters. This is the ocean depth that's measured by that buoy. And we can see oscillations on the order of maybe 60 centimeters or so. Who can tell me what that's caused by? Tides, right? So we can see here every day we have a low tide, high tide, low tide, a minor high tide, so on and so forth. So that's the tidal wave. This is the measurement on March 11th, 2011. Again, we see the signature of the tidal waves. But then here, those are the oscillations caused by the tsunami as it went past. And again, you can see the amplitudes aren't any larger than the tidal waves. And yet we saw that there was a 2.5 meter amplitude wave as it rushed into the harbors around Hawaii. So that's great. We can use these buoys, and they can give us some warnings, some monitoring of whether or not a tsunami has been generated. We're not going to be able to do that until the tsunami actually passes the buoy, so the correct location of those buoys is important. And then knowledge of the ocean bathymetry, so that's the altitude profile of the ocean surface underneath the ocean, can then allow us to predict the arrival time of the tsunami as it goes across the ocean. And that's pretty good these days. And that can allow us to detect and quantify whether or not we should be concerned about this tsunami. But buoys are expensive. They require a real-time data linkage, and they're somewhere in the middle of the ocean, so that requires a satellite link, which can be expensive. Buoys go down all the time. I just looked the other day, and about 30% of those buoys that I showed you on the map are currently not transmitting data. Not the best for a critical warning system, if you ask me. And the other question is, if the tsunami is closer to land than it is to the buoy, the tsunami is going to reach land before you actually monitor it. Okay, so there's clearly a need for some other sort of monitoring system out there that won't have all of these downsides. Now, of course, these buoys are great. They do their job when they're running. All right, so let's talk about an alternate approach. All right, so this is from a paper that sort of started it all back in 1976 by Peltier and Hines. Detecting tsunamis by monitoring the ionosphere, and I'll tell you what that is in a minute, combines 3 elementary facts. A tsunami must displace the atmosphere as it propagates across the open ocean. The atmosphere responds to this excitation by propagating what are called gravity waves, obliquely upwards. And these waves grow nearly exponentially with height as they proceed into the rarefied regions of the upper atmosphere. I'll explain what all those 3 statements really mean in the next few slides here. But this is the basis for the use of space measurements to monitor and maybe predict what's going on the ocean surface. All right. This is the Earth. The Earth is surrounded by different levels of the atmosphere: the troposphere, the stratosphere, the mesosphere, the thermosphere. All right. If we look here on the left, it's a measurement of the temperature. So you can see how temperature changes as you go up into the upper atmosphere. This is in Kelvin. But more importantly here, I want you to concentrate over here. This is, as a function of altitude going up in the atmosphere, the density of different molecules and atoms in the atmosphere. And so you can see here, this is our neutral atmosphere: oxygen, nitrogen, oxygen molecules. And we're very, very, very dense. Lots of molecules, lots of atoms here near the surface of the Earth. But as we go up in altitude, the atmosphere gets more rarefied. That means the density goes down. And it drops by several orders of magnitude. Again, this is a log scale. So these are several factors of 10 in terms of density as you go up. Now, located in the same region as we have this neutral, we also have the ionosphere. And the ionosphere is characterized by the electron density. And so because the sun is there and the sun has energy that can ionize your neutral atmosphere and knock off some electrons, and they can coexist in this region called the ionosphere. And the peak in the electron density typically occurs around 300 kilometers, 350 kilometers in altitude. It's about the same altitude that the International Space Station flies at, to give you some reference. And so these are two important things. So one is that we have electrons that we're going to be able to make use of when we need to make some measurements. And then the other is that the density of the atmosphere decreases as you go up in altitude. Those are the two things I want you to take away from this plot. Okay, so let's take a look at what happens with an earthquake. So an earthquake will shake the atmosphere. So you have an earthquake, you get some rupture, and that's going to push, like a piston, the air above it. And you're going to get these waves propagating up into the upper atmosphere. And you can imagine as that compressive air moves higher and higher, it's going to move the atmosphere as it moves through the space. And so within tens of minutes, 10 minutes or less probably, that initial shock from the earthquake is going to reach all the way to that altitude layer, 350 kilometers or so, where we have lots of electrons. You're also going to get a Rayleigh wave that's going to propagate along the surface. And again, that wave is going to create waves that propagate upward into the atmosphere and is going to disturb the electrons at 300 kilometers above. So how can we make a measurement of that? You know, we have some wave and it's moving electrons, but those electrons are very, very, very small and they're 350 kilometers away from us. So how can we go about measuring it? That's a really difficult altitude range to measure. It's too high for balloons. You can fly a rocket through that region, you can get to that altitude, but you can't really just launch a rocket on a whim or very rapidly. You have to plan for it. And it's too low for a satellite to fly through. Most satellites are at 500 kilometers or higher. So it's really this region where we have to do remote sensing. If you're here for Professor Carney's lecture 2 weeks ago, he talked about tomographic imaging and how you can use light to measure properties about regions that light is traveling through. That's a remote sensing technique. So what I'll show are the results from making use of GPS. So the Global Positioning System, we all probably have a GPS receiver in our pocket. Most cell phones have GPS receivers in them these days. And as it turns out, that revolution in GPS has given those of us who are interested in the remote sensing of the upper atmosphere this wonderful tool to use to measure the movement of those electrons. And the reason this is because as you propagate a wave through electrons, because that signal that is carrying the information you need to calculate your location is carried on an electromagnetic wave, as it travels through these electrons, those electrons are going to move in response to that wave as it goes through. And that's going to slow down that communication signal a little bit. All right? So we get one wave coming through and it's slowed down a little bit. That's not terribly useful. However, if you have a second signal that comes through and it's at a different frequency, it's going to be slowed down by a different amount. And so if you can measure the difference in the arrival time of this first signal and the second signal, you can come up with a very accurate measurement of how many electrons those signals move through. Very accurate. And so this is called, this is a dual frequency receiver because we have to be able to measure these two different frequencies. And it allows us to come up with an estimate of the integral, the total number of electrons. So we call it the total electron content of the ionosphere. Fortunately, there are about 12 GPS satellites overhead at any given time. So you have measurements in 12 different locations. You can use GLONASS, which is the Russian version of GPS. And soon, if the European Union gets more satellites launched, you'll have Galileo up there as well. So you can make measurements to all these different satellites that are above. The satellites are moving, so that gives you some sense of spatial relationships. And then if you have a large network of these receivers, you can start to put together images of what these waves might look like in the ionosphere. So this is Japan. And this is on the morning of March 11th, 2011. Japan obviously is very concerned about earthquakes and tsunamis, so they have a network of about 1,200 to 1,500 GPS receivers that can make this exact measurement. And so we can make from these 1,500 receivers to 8 different satellites, you can start to put together maps like this. So you can actually see little shadows of the Japanese islands here, right? And so that's all the receivers on Japan looking to the west at a satellite and making a measurement. And then we're looking to the southeast and making a measurement. Okay? And what we have plotted here, and this is actually the result of one of the classes that we teach here at ECE Illinois in Big Data, are the changes in the number of electrons that are measured by these GPS receivers. And so remember, this is a measurement in space, 350 kilometers above. And hopefully, now we start to see the satellites are moving, which is why we get this motion. There's the earthquake. And then we start to see this rippling in the number in the electron density. And that's this acoustic wave propagating up and moving those electrons. And now we're making measurements through that electron density of those changes. And so we can see very concentric waves, just like if you threw a pebble into an ocean, it ripples out. And that's what we're seeing here. And so again, this is the earthquake effect. It's not the tsunami effect, but it's the earthquake effect. We can actually use this total electron content technique to measure lots of other things. There's the US. These are the Moore tornadoes from 2013. A lot of energy is being dumped into the atmosphere, generating these sorts of waves. And again, we can see concentric rings emanating from the region where we have all this activity in the lower atmosphere. But we're using measurements 350 kilometers above to study these. What else can we do? This again is back in Japan. Here we can see over here, we see this little blue streak going through the total electron content. What country is this? North Korea. What is North Korea trying to figure out how to do? Launch missiles. This is the signature of one of their ballistic missile tests by making use of total electron content measurements. There are also studies out there, underground nuclear detonations we can see in the ionosphere by making use of this technique. So actually the UN, the Comprehensive Test Ban Treaty Organization, they're interested in these sorts of observations as other ways of making sure that people are living up to their obligations under the CBTO. Okay, tsunamis. They're also going to do the same, right? We're going to have the tsunami wave, long wavelength, periods on the order of tens or 20s of minutes. They're going to move through. It's going to push up. It's going to create a slightly different type of wave, which I'll talk about, called a buoyancy wave. And that wave is going to oscillate and propagate vertically. And it's going to enter into the upper atmosphere, and we're going to generate these sorts of waves. And if we can measure those oscillations in the electron content or some other proxy, we'll be able to come up with some observations that we can relate then to the underlying ocean wave. So what is an atmospheric gravity or buoyancy wave? Essentially, imagine you have a parcel of air here. Now remember, the density increases as you get towards the surface. It decreases as you go up in altitude. So if we take this parcel of air that's at equilibrium, it's where it should be, and we push it up, it's now going to be heavier than the air surrounding it. So gravity is going to want to pull it down. And so gravity will pull it down, but it's going to overshoot. And now it's going to be at a location where it's too light. And so buoyancy is going to push it back up. And so we're going to get this nice oscillating, like you had a weight on a spring and you just let it go and it will oscillate. And so we're going to have this buoyancy wave, and this parcel is going to move the air above it, and it's going to move the air above it. And so we're going to have this wave that's going to be able to propagate all the way up into the upper atmosphere where we might be able to make observations of it. Okay. Importantly, right, because again, the amplitude of that wave on the ocean is very small, tens of centimeters. Because the energy in that wave as it propagates upward has to be conserved, it has to stay the same, the background density is getting smaller and smaller, and so the amplitude of that wave is going to get larger and larger. So what starts out as 10 centimeters on the ocean surface grows to tens of kilometers as it gets up to 300 kilometers or so. And that tens of kilometer oscillation is large enough for us to see with this TEC technique. And so this growth of several orders of magnitude allows us to make this observation and relate it back down to the ocean wave. All right, so this is 2010 earthquake in Chile. This is the model of the tsunami that was generated. Here we have observations made by that buoy. And we have the blue are the actual observations, and the red is a model. that was generated to study this. And you can see the model does a very good job of tracking what actually happened, which is good. That wave is propagating. Here's time. So those are minutes and hours. So you can get a sense of the velocity that this is moving. And eventually it's going to hit Hawaii. And again, as it's moving, it's pushing the air up and generating these waves that are propagating all the way up into the upper atmosphere. These are the measurements of the total electron content made by the GPS receivers on Hawaii. And we can see these bands of red and blue in these two groups of satellite pierce points, which are indicative of this wave traveling through the total electron content caused by the underlying ocean. Okay? And you can go back, and this is a colleague of mine, Lucy Roland, and what she's done is she's gone and back and looked at all the historical events in the Pacific and Indian Oceans when GPS receivers were deployed, so the past decade and a half or so. And every single one of them, you can see these bands of blue and red, which are indicative of these waves. And so there's clearly a signature in the upper atmosphere caused by the tsunami waves. The difficulty, though, compare this to the map we had from Japan, where we had a high density of GPS receivers, and we could actually see the waves, right? You could actually see the concentric rings emanating out from the earthquake. In the US, where we have lots of GPS receivers, you could see the waves emanating from the tornadoes. Here, because we're in the open ocean, and there's only so much landmass we can use to put a receiver on, we don't really get that image that we would like to be able to use to be able to determine the properties of the tsunami. Okay? So this is the problem with using the GPS technique for the tsunami problem, because we're interested in something over the ocean where by definition there's not a lot of land mass, and so we don't get an image. Okay, so the sparseness of measurements over the ocean really limits the utility of this GPS technique. So what else can we do? All right. What's that? That's the Earth. Okay, let's see. You are here. That's Chicago. That's 57. That's 74 to Bloomington, 72 to Decatur, Danville, our friends in West Lafayette, and Indianapolis. Okay? These are pictures taken by astronaut Don Pettit from the International Space Station using a Nikon DSLR camera that you can go out and buy from Best Buy if you want. And he was up there for quite a long time, and he set these up to be able to make these measurements of Earth and give us all a sense of the world that we live on. So let's see, what else can we see here? All right. So clearly looking down at the Earth, there's sunrise. We can see lots of things we recognize. There's the moon, by the way. We can see lots of clouds. We can see lightning now and then. But I want to draw your eye to this. So those are the northern lights. Okay, we're pretty familiar with that. And we're used to the thought that due to some photochemistry in the upper atmosphere, at high polar latitudes, we can generate light. And that light has some relationship to what's going on in that upper atmospheric region. But what I want to show you is there's actually this layer of light that surrounds the Earth. Okay, so it's not just at northern and southern latitudes where we have the aurora, but it's all the way around the world. And you can see there are different colors. There's red, there's green. If you understand the chemistry behind the emission of those lights, and you have a camera system, you can all come up and take a look and I'll tell you more about it. You have a camera system that is, there's lightning, I love that. You can use that layer of light that's being emitted as your sensor. And so as a wave goes through that layer, it's going to perturb the amount of light that's being emitted. So you're going to have dark regions and bright regions, just like in the electron density we had red and blue with the increase and decrease. And so as those waves, those buoyancy waves, gravity waves go through, if we have a camera system that can make a measurement of that layer, we should be able to see that wave. This has been hypothesized, but until 2011 it had never been observed. So here's the Tohoku earthquake. And it generates a wave that goes all the way across. There's Hawaii. Since about 2001, when I was a grad student, I had deployed one of these imaging systems, an imaging system just like this, up on the top of the Haleakala volcano on Maui. We were studying something completely different, some other completely different physical phenomena. But we take data every night, and this wave happened to go by Hawaii when the sun was down, so we were taking measurements. And so my program manager at the Office of Naval Research, Bob McCoy, called me up and said, hey, there's this guy in France, Philippe Lejeune, who has been looking for this signature of the tsunami in the upper atmosphere. Go take a look at your imaging data and see if you can see it. And that began an odyssey of 2 months of no sleep because I was doing round-the-clock observations and I was collaborating with my colleagues across the ocean, and everyone was always up at all hours. And I had a 1-year-old, but were we able to see? So this imaging system provides a map. The gray is the intensity of the light. And so you can see that we have regions with dark and bright. This here is a model of what's going on the ocean surface, and this red line that you'll see is basically tracing the front of the tsunami. Okay? So as we see here, every about 5 minutes or so, we take an image of this air glow layer, and here we start to see waves, dark and light. They're aligned with the wave on the ocean, and they're moving with the same velocity, in the same direction. We did all the measurements you would want. They had the same wavelength, same period, everything like that. So this was pretty much conclusive evidence that sure enough, you could see these gravity waves by using a camera system on the ground pointed up. And what's important here is, whereas with the GPS technique, as we saw, you need to have lots of receivers. With this, with a single camera, we're getting a 1,000 by 1,000 kilometer region that we're observing. So this acts like 1,000 GPS receivers. But you only need a single one, so you can put them on islands and still get a very large range of observations. That would be great if it only worked once. It would be even better if it works twice. So this is the Haida Gwaii earthquake, a much smaller earthquake, and I won't get into this, but this is something we're working to understand now. Here we have passing Hawaii, and there you go, waves, traveling in the exact same direction as the tsunami, exact same wavelength periods, all those sorts of things. So very clearly related to what we're seeing on the ocean surface. And you can see there are other clutters like clouds and things like that. That's a problem with making observations on the ground.
How do clouds affect?
Exactly. So we're looking in the visible. We're looking at red light. So if there's a cloud in the way, we don't see anything. Okay? And this is one reason why we go on top of volcanoes that are 10,000 feet. And there's fewer clouds that we have to deal with, but it's not perfect. Other problems, if the moon is up, that's a lot of light. Those air glow layers are very, 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 very dim. So the moon swamps us. So there are problems. And I'm going to talk about, boy, I'm running out of time. I'm going to talk about some of the ways we're thinking about solving these problems. Okay, but that's a very good question. Okay, so these measurements demonstrate the utility of making observations of the upper atmosphere to understand what's going on in the ocean. Some of these properties appear to be tightly related, but the amplitude has murkier relationships. It's not a one-to-one that we see 10% variation in the light corresponding to 20 centimeters oscillation on the ocean surface. There are a lot of confounding factors there, which we're working on in ongoing research.
Can you just move out of the visual spectrum?
You could. It depends on if you can find a wavelength that is being generated by the photochemistry in the upper atmosphere. So there are some infrared emissions you can think of, but infrared doesn't get down to the ground. So let's go to space. That's my last slide, so you know. But we really need to have some physics-based models to be able to link some of those properties that aren't clear to us at this point. So what we're doing now is we're starting to generate these models. So if we have a model of the ocean, which I've shown you that some people do, you can have this tsunami propagation model. You then need to couple it into a model of the atmosphere so that you can propagate this gravity wave through a realistic atmosphere. Because depending on what the winds are doing and the temperature is on a given day, that propagation is going to be different. You then need to have a model that couples the neutrals, those oxygen, O2, N2, into the plasma, the electron density. You then need to have a model that tells you what the air glow emission is from the chemistry. And then you need to have a model of what your imager does. Okay, so this is really exciting because previous to this, I had been working in my one little domain looking at that. right? But now I have to start learning something about ocean physics, something about lower atmosphere, something about photochemistry, something more about photochemistry, I should say. So it's this really interesting, just eye-opening experience to be able to see how the entire Earth and Earth space, geospace, is coupled together. We've made some progress. So this is actually using a different type of wave, so not the tsunami wave, but a convective plume that one of my colleagues, Sharon Vadas, provided us. She works out in Colorado and does a lot of this gravity wave propagation work. And she had been modeling how thunderstorms propagate these gravity waves, much like those tornadoes that we saw in the TEC. And so we took her model and we started working at coupling the neutral, the winds, and the densities into changes in various ion and electron species. And they're time dependent, so you can see how these changes in the wind fields push ions and electrons around, and you can see it's not symmetric when you get to the electron densities. These are some of the compounding factors I was talking about. And then we've generated the models where you can then simulate what an imager would see for this. So what we're working on now is actually replacing that convective plume, that thunderstorm model as the source, with the ocean. And that means Sharon needs to learn a little bit more about the ocean so that she can go that final 5 kilometers down to the surface of the globe. All right. So we're starting to make those strides to be able to come up with this model that would be able to tell us how those oscillations in the air glow relate, depending on where you are and when you are, to what's going on the ocean. And what would be really nice is if we could put one of these imaging systems on a satellite, say on a geostationary satellite, where communication satellites tend to fly. This is the view from GOES West and GOES East, which are geostationary satellites that do terrestrial weather. And you can see from a single satellite, we would basically be able to see the entire Pacific Ocean. And some of the Atlantic, if you used a satellite further to the east, you could see the entire Atlantic. But from that single vantage point, you would be able to see the entire ocean. It wouldn't be dependent upon where the buoy was located. Since it's up in space, it wouldn't be dependent on whether it was daytime or nighttime, whether it was cloudy, rainy. Actually, there are blizzards up on the volcanoes in Hawaii today, so you can even get snow up there. And so it takes out a lot of those factors that from the ground we run into. But if we could work out the physics and convince people that we could make use of these sorts of observations, we would have essentially a real-time monitor for the entire ocean from a single platform and be able to essentially instantaneously, once we see those observations in those airglow layers from the spaceborne platform, be able to come up with a more robust monitor and prediction of whether or not we need to evacuate coastlines. So I think I'll stop there. I'm happy to answer any questions, but thank you.
So, Jonathan, thank you very much. So, first of all, Brady, are you here? Brady? Brady? No. Okay, hang on. Would you go grab, do you know Brady Saltz? Go grab Brady and tell him to come on in. So, are there any questions? Questions from the audience? Right here.
The actual motion of a particle in the ocean as a tsunami goes by. You are swimming in the ocean somewhere far from anything.
Yep.
Miles above the floor.
Yep.
And during the half hour it takes for the tsunami to pass you, how far do you move?
Okay, so the question is what the motion within the ocean, so the motion in the ocean, of the particles of the partials of water, and how that happens as the tsunami goes by, and what you would feel if you were swimming there. So the tsunami does set up circulation cells that are fairly deep. And are essentially, I think, the wavelength of the wave, so very, very large as well. You would feel yourself going up and, well, actually, no. You wouldn't feel yourself going up and down. You would maybe feel a little bit of motion. Right, and this is actually one of the important things about the being able to predict when the tsunami is going to get inland before the tsunami actually gets there, because what the Navy will do and what fleets of vessels will do is they'll actually go out into the open ocean. Because then you just go up 10 centimeters over a half hour and back down.
How far sideways in the direction?
You're not actually going to be moving. You're not going to be swept up in that wave. You're just going to go up and down. You're not going to move, you'll move a little bit, but you're not going to move 100 kilometers with it.
Do we have other questions? So
Right here, up front.
So how much was the time delay from the actual wave up to like where you're sensing it?
Good question. So the question is, what is the time delay from the source on the ocean to where we would be able to sense it up in the upper atmosphere? Depends a lot upon the properties of the atmosphere on that day, but a good ballpark is the earthquake, the acoustic wave caused by the earthquake takes about 10 minutes. The gravity wave, it takes about 45 minutes to propagate upwards, but once it's there, you saw in the airglow images from the Tohoku event, the black and white, the waves actually were ahead of where it was on the ocean. So once it gets up into the upper atmosphere, it has a little bit of leeway to go a little bit faster or slower, depending on what's actually going on up there.
And then the detection is only at night? Or during the day as well?
Okay, so from the ground, it would be during the night only. There might be some filtering techniques you could do to do daytime. But from space, if you were looking at infrared emissions and the like, which you can do from space, you would be able to do it 24/7.
okay. Right here?
The slide that you had of the tsunami going through the field.
Yes.
How many miles inland did that go?
On that specific one, I can't quote you because I don't know the topography of that region off the top of my head. But essentially, any region of land that is below the amplitude of the tsunami as it reaches shore and is less than that wavelength, so 5 miles or even longer, can be affected. As you get in, say, a fjord or something like that, you can get a channeling effect, and it can go even further inland from there. Okay.
We had a question right here.
Yeah, it's a brilliant idea to use the airport, but as you point out, there's a lot of complicated couplings.
Of course.
The more direct measurement would be directly remote sensing the signal. Is that not possible?
That is possible. You can actually use reflectometry and things like that to measure surface roughness and things like that. One of the difficulties of those sorts of measurements is just the wavelength, the wavelength of the wave on the ocean surface. You'd have to have lots of, or several measurements across that. And if you had, say, TOPEX or Poseidon, which is an altimeter satellite that bounces waves off the ocean, it's only going to be measuring a cut across that. So, you know, every technique has its advantages and disadvantages, and really the solution is to put all of those techniques, or as many of those techniques as you can afford in budget-constrained times, as possible, so that you can leverage the pros and mitigate the cons of each one of them.
Right here?
Can you give us some sense of what these models that you're running look like? They occupy the supercomputer for hours at a time, or is it something you can run on your laptop?
Yep. So there are different types of models we're working on. One, we have one that is just purely geometry based. And you can figure out whether, once you know the orientation of the tsunami wave, you can almost instantaneously know whether or not you should be able to see it. And this couples into the coupling physics between the neutrals and the ions and things like that. If you really want to have a deep understanding of the physics all the way up, you're getting to supercomputer space. And so this is Sharon Vadas at Colorado Research Associates. She makes use of some of the supercomputers operated by the National Weather Service and NASA and the like, I believe. But this would be a perfect problem for, say, Blue Waters here on campus.
Right here? And get you next.
Are these models actually used in operation now? No. No. So we are still definitely in the research phase. We're 2 years into a 4-year program. I'm not going to promise success in 2 years, but we're working on it.
How close to shore are boats inevitably swept up in the wave that goes towards shore versus going just up and down?
That's a very good question, and I don't know the answer to it. I don't know. I know they need as much leeway warning as they can, so they can get as far out as they can. I think I saw one video. YouTube is great. I saw one video from a Japanese vessel that was maybe a couple miles off the coast, and it was noticeable there. So I think you want to be more than that, at the least.
Right here.
There's constantly so many earthquakes happening underwater
Mhm.
like in, Hawaii, DC. What is the minimum Richter scale that causes the tsunami?
Mhm.
Do you have a level?
So it's dependent on lots of things. It depends on the type of earthquake, right? And you have ruptures like that, you have ruptures like this, and so you need to displace water, right? So usually the folds like that are going to be more effective because you're actually going to be pushing the ocean column up. So this is why I said the detection of the Richter scale doesn't tell you everything. You need to actually make that observation on the ocean surface. The Tohoku earthquake was a magnitude 9. Okay, so clearly that can generate tsunamis. The Haida Gwaii was a magnitude 7.2, thereabout, so 2 orders of magnitude less energetic, and that created a tsunami. There have been several, there was 1 or 2 in Chile last spring, I think, and they had the magnitude, 7, 8, 9 even, I think one of them was, but they canceled the tsunami alert within an hour or 2 because there were no observations. So if you actually look at the Pacific Tsunami Center, they put out these bulletins, and within the first few hours they say, a potential tsunami generating earthquake has occurred. Take precautions, but keep monitoring, and until you have a couple hours where you haven't seen any sort of wave, we're not going to cancel it. Okay, so it's not just a function of the magnitude of the wave, it's a function of the earthquake, it's a function of location and the type of the earthquake as well.
What's the prediction for the height and inland distance of a wave that comes from the Canary, half a Canary Island?
That's right. That's the big one, right? Because that will wipe out Boston, D.C., New York, and all those, right? I've seen those Discovery Channel shows. I don't know how far inland it's going to reach or anything like that off the top of my head. No, but I know that's one of the common for the Atlantic Ocean where it's not so seismically active. The landslide from the Canaries is one of the potential problems.
Okay, so I'm going to exercise presider's privilege and ask a question or two myself. We have what looks to be a camera.
Yep.
Up here, so you want to tell us a bit about this, and can folks come check it out?
Yeah, that's why I brought it down here. So this is one of the imaging systems that we designed when I was at the Naval Research Lab in those 2 years. And it's significantly smaller than the ones that we had used in the past. I was getting tired of schlepping along something that was as tall as me, so we compressed it into something that you can carry along in your carry-on suitcase. But if you're interested, I'll come and explain it to you. I also have some of the filters that we use to isolate the emissions that are created in the upper atmosphere so that you're only looking at the chemistry you want to be looking at. And I'm happy to go into whatever details you want if you come up here after.
Okay, and I'd like to suggest that Jonathan will stick around a little bit.
I will.
And we'll take more questions just up front after this is over. I'd like to thank everyone for coming. We normally like to have some stuff to give away to the kids in the audience after this, but we have a building full of that going on right outside here. And so, for instance, actually, could I borrow this for 1 second? One of our students, whom Jonathan and I advise, actually, and works with us in teaching, built a bunch of these little lapel pin kits. And for the younger kids in the audience, sort of 13 and under, we've got some of those, I think, actually already built out there. Did you guys build this one yourself? So if you want, you can go finish soldering the final pieces on this and discover the joys of burning your fingers on a soldering iron and what it's like
That's right.
to be an electrical engineer or a plumber. We'd like to thank all the kids out there who have made this a great day on campus for all of us. I'd like to thank Jonathan again. Thank you very much, Jonathan.
Thank you.
Illinois.